Hello everybody. Now after the perception algorithm does its job, next comes decision making and trajectory planning, and in this video we are going to discuss extensively about decision making and trajectory planning. As the name itself is self-explanatory, you after the perception is completed, the perception algorithm does its job, then the computer or the ECU takes a decision and it plans a trajectory. Okay, let's further elaborate. Now autonomous vehicles and advanced driver assistance systems rely on integrated decision making and trajectory planning systems to navigate complex environments safely. All right. Now, these systems process real-time sensor data, environmental context, and vehicle dynamics to generate driving strategies and precise motion paths. This word is extremely important. Precise motion paths. The more precision is involved, the better the drive is, the more reliable the autonomous driving is. Now, coming to the decision making system, the decision making layer translates perceived information into actionable driving strategies through what is the first input? Input is environmental data, HD maps, and ego vehicle status. All right, and the environmental data, of course, it involves the obstacle, the position, the speeds, the traffic signs, and the HD maps which are inbuilt, and also the ego vehicle status, which includes the location and the velocity. Next comes the outputs, which is high level behavior, lane changes and mergers, and low level commands, acceleration, steering angles, and methods. And what is the method? Rule based system use predefined logic for predictable scenarios. Now, learning based approaches. What is the learning based approach? SVM and deep learning model handle complex interactions, achieving 86 plus accuracy in lane change decisions. Of course, this particular accuracy is a ballpark figure, and I am sure this percentage will definitely improve as the technology further progresses. Now, coming to the optimization frameworks, balance safety, efficiency trade-offs using cost functions. Now, key challenges include real-time processing and handling edge cases like sudden pedestrian crossings. Okay, so this is the biggest challenge to, as the decision making becomes more accurate, it needs to process more amount of data. But the challenge is that may increase the latency or that may enhance the lag. But despite the more decision making and decision more processing, the time processing should be kept less than 100 milliseconds, and this is the biggest challenge. And this also leads to the handling edge cases like suddenly pedestrian crossings. Okay, now coming to the motion planning architecture, modern systems decompose motion planning into two interconnected layers. The first layer is tactical decision making layer, which determines driving maneuvers through scenario classification. For example, a T intersection is there, or a three road junction is there. All these things are categorized with the help of scenario classification. Now coming to the risk aware behavior selection using probabilistic prediction. So, with the help of probabilistic predictions, it clearly judges the risk. And last but not the least, multi-modal decision generation. For example, overtake versus follow, whether you have to overtake a car or you have to follow the car. All these things are clearly judged. Now, when it comes to trajectory generation, it creates dynamically feasible paths using, this is complex integration equation, so I won't want to trouble you because this appears very complicated integrated differential calculus, so I won't trouble you. Just understand that there is a certain complicated mathematical equation to understand the trajectory. Okay, and this trajectory is subjected to vehicle dynamics constraints. And what are the vehicle dynamics? It may be the acceleration or deceleration or mass of the vehicle. All the kinematics of the vehicle are taken into consideration. Now, what are the trajectory planning techniques? Okay, we will see the method, we will see the advantage, and we will also see the limitation or the cons of the vehicle or the cons of that method. The first this one is method is sampling based RRT. Now, I will tell you what RRT stands for in the coming slides. But as of now, you note down that sampling based RRT is a very predominant method, and the advantage is it covers completely the scenario, the decision, the pedestrian, all these things it covers very extensively. But what is the limitation? The limitation is high computation. And when optimization based model, predictive control MPC, model predictive control, Advantage is dynamic constraints and it is very locally minimized. Disadvantage is very locally minimized. Now coming to the hybrid GNN optimization, the 62% planning and training data dependency is the limitation, because how much data it can recollect depends on how much you train the particular GNN. Alright, now when it comes to the decomposed geometry kinematics, the advantage is real time capable and it is limitation is suboptimal coupling. Now recent advances combine graph neural networks for initial trajectory prediction with numerical optimization for constant satisfaction, achieving 3.26 seconds planning times in unstructured environments. Alright, so this 3.26 seconds is considered a very minimum time, but again, as I said before, as the technology progresses, this is going to further come down. Now, how is the decision making and trajectory planning going to be integrated into ADAS? Alright, the order of the integration or implementation is: first is emergency collision avoidance. First, the trajectory should ensure no collision should happen, and this is done with the help of risk optimal stopping location selection. Alright, next comes the adaptive cruise control, which is MPC based spacing maintenance and traction adoption, friction aware replacing for icy roads. And also the fail-safe trajectory, which is a quintic Bezier curve. This is a very complicated mathematical curve, so I request you not to go into this. It's a very acoustic based quintic Bezier curve with 50 heads update rates. Now these systems demonstrate 94% collision avoidance success in stimulated critical scenarios through the challenges remain in the sensor fusion latency and corner case generalization. Now current research focuses on physics involved in neural networks and risk aware reinforcement laying to bridge this gap. Now this fail-safe trajectory is extremely important. I request all of you to study this if possible in Google or anywhere any other material to understand thoroughly. Now we will see in detail the decision making and trajectory planning, motion planning for autonomous vehicles and ADAS functionalities. Now autonomous vehicles and advanced driver assistance systems rely on sophisticated algorithms to navigate safely and efficiently. Alright, the key components involved are the decision making. It determines the vehicle's high level actions based on traffic rules, obstacles and goals. Alright, it clearly determines vehicle's high level actions based on traffic rules, obstacle and goals, and it also uses input from perception. Okay, and what is the how does it perceive? With the help of sensors like camera, lidar and also localization, GPS, HD maps. Or for example, when it comes to lane change detection, whether to overtake a slow vehicle; when it comes to intersection handling, deciding when to stop or proceeding; when it comes to obstacle avoidance, reacting to the pedestrians or sudden obstacles. So these are all various examples of decision making. And what are all the techniques? Including the techniques which I mentioned in the previous slide: the rule based system if else logic for traffic scenarios, machine learning reinforced learning from driving data, and behavioral cloning imitating human drivers. Alright, so this whole thing is comprising of decision making. Now let's see the trajectory planning. The trajectory planning involves generating a smooth collision free path for the vehicle to follow. And now it considers the kinematics, considering the kinematics which involves including judging the steering angle, understanding the acceleration limits. Okay, judging the steering angle and also understanding the acceleration limits comprise of the kinematic consideration. And coming to the dynamics, friction, vehicle stability, all these things are extremely important. Now how is this what is the method of trajectory planning? Now there are plenty of generating the polynomial equation. This is called polynomial trajectory, whether it is quintic or cubic splines for smooth curves. So understanding a clear cut the polynomial equation and ensuring the vehicle is following the same polynomial equation, make sure that trajectory is planned in a smooth curve. and optimum control. When it comes to optimum control, minimizing jerk energy or time, sampling based RRT hybrid A for complex environments. Now coming to the motional planning. After decision making and trajectory planning, I want all of you to understand the path. First you decide, then you plan the trajectory, and then finally you plan the motion. And now what does it do? It is combined decision making and trajectory planning. Underline this word, it combines. It combines decision making and trajectory planning to generate real-time executable paths. It ensures vehicle follows the traffic rules while avoiding collisions. This is important. The path cannot be generated based on any random rule. It must follow the traffic rule. For example, it must overtake only from the right. When there is a traffic signal and where there is a red light is blinking, you should stop at the traffic signal. Whenever you are taking a right turn, it should show a proper blinker. You should show a traffic signal that you are making a right turn. All these traffic rules must be meticulously adhered to. Alright, and this motion planning ensures that traffic rules are meticulously adhered, and it also makes sure that no traffic rule is violated. Now coming to the approach, friend frame, model predictive control, and graph search method like A star for global plot planning, Digikstra, optimizing trajectory for receding horizon, all these things comprise of the motional planning. Alright, now to proceed further, ADAS functionalities using this. What are the various ADAS functionalities which use these concepts? Now ADAS features lever, simple algorithms, but simpler implementations. Now when it comes to ADAS, adaptive cruise control, which includes both decision making, it adjusts the speed based on the leading vehicle, it also plans the trajectory, smooth acceleration and deceleration. Now when it comes to lane keeping assist, motion planning involves using freenet frames to stay within the lane boundaries. And also automatic emergency braking, decision making includes detecting collision risk and triggers braking. Now when it comes to autonomous parking, it uses hybrid A or RRT for type space trajectory planning, and RRT stands for rapidly exploring random tree. It is an algorithm which is a motion planning algorithm widely used for autonomous vehicles due to its probabilistic completeness, meaning it can find a feasible path even with many samples. Now RRT builds a tree structure by incrementally exploring the state space, starting from designated route node and expanding towards the goal. Okay, understand this very carefully. By incrementally, this is a very important. RRT builds a tree structure by incrementally exploring the state place, starting from designated route node, expanding to the goal. So in short, this is like identifying a starting point A and going to end point B with a clearly generated polynomial, or whichever order of the equation is a clearly generated equation. Now when it comes to challenges, the real-time computation must process decisions in milliseconds. Now this is very important. Again I am emphasizing latency should be as less as possible, and uncertainty handling, dealing with sensor noise and unpredictable agents, and safety guarantees formal verification of planning algorithms. Now decision making, trajectory planning, and motion planning from core intelligence of AVs and ADAS. While fully autonomous systems require complex based system solutions, ADAS functionalities use simplified versions for safety and convenience. So ADAS functionality, when it comes to ADAS functionality, the equations are not as complex as for general traffic. They use more simplified versions, and future advancements will focus on robustness, scalability, and human-like driver behavior. All said and done, we want to reach the level 5 human-like driving behavior. So this is going. So the future advancement is focusing on the robustness, scalability, and human-like driving behavior. Now we will see in detail how machine learning and statistical analysis contribute to data-driven decision making in ADAS. Alright, now coming to the machine learning and statistic analysis, they form the backbone of the data-driven decision making in advanced driver assistance systems, enhancing safety and operational efficiency through three key mechanisms. What are the three key mechanisms? First is sensor fusion optimization. No prizes for guessing. First is of course sensor fusion optimization, and the machine learning algorithms. It integrate data from cameras, lidar, radar, and ultrasonic sensors to reduce false positive by 50% and false negative by 62.5% compared to traditional methods. Now it also improves object detection accuracy to 93% using lightweight convolutional neural networks like MobileNet V2. Now this is the off-the-shelf CNN, and it also enables real-time processing with 25% faster response time, where response time is reduced to 15 milliseconds when compared to the 20 milliseconds. Now, deep learning models process multi-modal sensors estimates to estimate object trajectories and predict collisions, forming the basis for emergency braking and lane keeping systems. All right, decision making enhancement and statistic frameworks optimize ADAS responses through extreme value theory. This is the first statistic framework, extreme value theory, and it models the rare events to calculate collision probabilities and validate against crash statistics. Okay, let me give you an example of extreme value theory. For example, you have a dash cam. A dash cam, if it records everything in the traffic, it may totally consume up or eat up the bandwidth. But with the help of extreme value theory, only accidents can be recorded. That's where this extreme value theory comes into picture. Alright, now next comes to the sequential testing. It monitors system performance in real time, triggering safety interventions when predefined risk thresholds are breached. Now coming to multi-criteria decision models, combine evidential reasoning with reinforcement learning to balance safety, comfort, and traffic rules. Now these are the three methods which enhances the decision making, and this method also reduce the latency by 40% while improving the accuracy to 85%. Now coming to the safety validation and adoption. Now statistical analysis addresses edge cases and system reliability. Alright, and now what does this statistical analysis comprise of? First, it comprises the subset simulation. It estimates failure probabilities 100 times faster than Monte Carlo methods for scenario testing. Now this Monte Carlo method is a very extensive method for scenario testing, but this subset simulation, it definitely takes up the simulation a couple of notches higher, and it enhances the probability identification 100 times faster. Now coming to the confidence interval modeling, it quantifies uncertainty in object creation, example plus or minus 2 meter positional accuracy, and it also enhances the friction aware replanning. And what is this friction aware replanning? Adjusts the trajectories using road conditions probabilities derived from historical sensor data. Okay, so these are all the various ways in which the fusion optimization, decision making enhancement, and safety method validation and adoption are completed. Now last but not the least, this digital twins is a modern method, state-of-art method, which further validates the system by simulating 10,000 edge cases before the deployment. Now these approaches collectively enable ADAS 1 terabytes of daily sensor data. Now 1 terabyte is an unimaginable amount of data. Okay, this much data it is capable to process while maintaining 100 millisecond response. 100 millisecond response time, and current research focuses on physics informed neural networks to bridge simulation to reality gaps in decision making. Alright, so let's see the technique, application, and impact. The first technique is, I'm talking about the techniques which is corresponding to MLT1 digital twins. The first technique is CNN based vision, and the application is pedestrian detection, and the impact is 94% recall in the low light. Text technique is Bayesian networks, and this application in risk assessment, and it has 30% fewer false alarms. Last but not the least, reinforcement techniques, and which is application is lane changes, and the impact is 86% human like decisions. Okay, so with this I am concluding this decision making and trajectory planning session. I hope all of you got a clear cut idea, a overview or a bird's eye view about the various ways and techniques in which the decision is made and also the trajectory is planned. Thank you. Thank you for your patient listening.